Hi, this is Physics 1, Chapter 14, which is going to be overheat. And as I go into this, there's a few things I want to mention at the beginning. First, what's called the thermodynamics zeroth law, and that is that when you have two things that are in contact with one another and they're at different temperatures, they will come to an equilibrium temperature. And what we're going to see with this is that with that, so let's say we have is a really hot metal ball. So this is a metal ball that has some temperature. Yeah, I'm going to say it's really high. And we put that into a liquid. And let's say the liquid is colder. So that's its temperature. Okay. Heat from this ball is going to transfer, or I should say energy from the ball is going to transfer from the ball into the liquid until all of this comes to one specific temperature. Alright, so for temperature, we look at the temperature as the proportional to the average kinetic energy per particle in a substance. Alright, so every one of these particles, both on the ball and in the liquid, are going to have their own kinetic energy, and there will be energy going exchanged between this ball and the liquid, but together you have so much energy in this and you have so many particles, and so that energy per particle is what we're going to look at as the temperature. The higher the temperature, the faster these particles are moving. Some particles will be moving very fast in this ball. They'll be moving extremely fast because they'll be really hot. They won't be moving as fast in this colder liquid, or I should say the majority of them won't move as fast in the colder liquid. And so the high temperature is what we think of as warm. So again, objects with two different temperatures in contact with one another will reach some equilibrium temperature. And we know naturally the warmer object will get cool. The warmer object's molecule will slow as it cools, as the energy is going from the hotter object to the colder object. And so you'll have a decrease in that kinetic energy, or loss of energy. Cooler object will get warmer. Cooler object's molecules will speed up, and you'll see an increase in your kinetic energy for the molecules. And so energy will be transferred from one object to another. The energy must be conserved. So this metal ball will lose energy. And let's say the amount E. And this liquid will gain E amount of energy. Okay. What this liquid gains, this metal ball has to lose. No more, no less. That transfer of energy is what we look at as heat. So heat itself is defined as the transfer of energy. We label heat with a lot of times a change in Q. And so it's just a change in energy, so it's going to be given with joules. We also give it in calories. 1 calorie is equal to 4.184 joules. This is more chemistry, but is another unit that you may see. A calorie is defined as the amount of heat necessary to raise the temperature of 1 gram of water by 1 Celsius degree. So 4.184 joules is the amount of energy to do the same thing. Then we have this equation for heat. And this chapter is probably the most important equation. Change in heat equals Cm change in temperature. Okay, so this is your change in energy. Okay. Delta T is your change in temperature. C is going to be your specific heat. And M is going to be your mass. Okay. Now notice with the change in temperature, if we have T final minus T initial, okay, if final temperature is higher, this comes out positive, which makes this change in energy positive. So positive Q, delta Q means an increased in temperature. And a negative delta Q is a decrease in temperature. Okay. An increase in temperature means an increase in energy. And a decrease in temperature means a decrease in energy. We also label this as a loss or gain. Right, so I'm going to go through the specific heat here soon. Before I get to that, I want to talk about what's called internal energy. The total energy within a substance is what we consider the internal energy. So, a substance contains different kinds of energy. They can contain translational kinetic energy, which is particles moving back and forward or in one direction. They contain rotational motion energy, so spinning around. They can contain symmetric stretching or asymmetric stretching. They can contain bending. They contain revolutionary energy or spinning energy. Just all different energies of motion, including energy with potential energy within bonds, all certain types of movement. So when a substance undergoes a temperature change, there is this change in internal energy. And so if we want to look at the ideal gas law real quick, the internal energy is equal to the average kinetic energy multiplied by all the molecules N. So N is the number of particles. So U is going to be labeled as the internal energy. This is equal to the number of particles times 1/2 m, then the average velocity squared. Okay, this is the average kinetic energy. We also had in the last chapter, based on kinetic theory, the average kinetic energy is proportional to the temperature. And here K is the Boltzmann constant. So this 1/2 mv squared equals 3/2 kT. Okay, and so from here, to bring up the little bar, you have this 1/2 mv squared, we can rewrite it as 3/2 kT, and then you're still multiplying by n, so we bring the n in. And then n is the number of moles times R, so we can rewrite this as 3/2 nRT. I should put NK there. That's where the K went. I just kind of dropped it there. There you go. Alright. So, in summary, I want to go through 3 things before we get into this example. Temperature is the measure of kinetic energy, average kinetic energy of the molecules. Internal energy is the total energy of the substance. Heat will transfer energy from high temperature substance to low temperature substance. Heat flows depends on the temperature and not the internal energy. So, if the temperature ends up the same, the internal energy can still be different because the temperature is measured based on the kinetic energy and not the internal energy. And if we are looking at something that has let's say a high internal energy but low kinetic energy, lower than another substance, the heat will transfer from the high temperature and not the high internal energy. Alright, so let me get to this example. Let me clear this page so I can have more clean space. Okay. We want to calculate the average velocity of 25 moles of oxygen, O2, at 500K. Right, so our temperature is 500K. Actually, I don't know, I put a 1 there yet. Let's see if I need a subscript or not. N is 25 moles. We're talking O2. Right, so we want to find the internal energy. Internal energy is U equals 3/2 nRT. R is equal to 8.314. And so we have U equals 3/2 times 25 times 8.314 times 500. Now, one thing I want to mention here is that this 8.314 is going to be giving the answer within joules, which is why we use it. If we use the other one, we have to figure out the units. Alright, so when we multiply this out, let me bring up my calculator. Right, 3 times 25 times 8.314 times 500 divided by 2. And you get 155,887.5 joules. Now this asks for the velocity. Okay, we want the average velocity. So this average velocity would be 1/2 mv r squared. So we gotta solve for this. First thing we gotta do is find the mass of this oxygen. So mass of oxygen equals to 25 moles times, this is 16, but we have 2 of them, so it'll be 32 grams. per mole. So 32 times 25 is 800 grams. And we are going to want to switch that to kilograms, 0.8 kilograms. Now, we want to set this equal, set our kinetic energy equal to 155,887.5. Right, so we have the mass, we just got to solve for V. So V R squared equals 2 times 155,887.5 over 0.8. That's your kilograms. This would be R equals square root of 2,155,887.5 over 0.8. So 2, oops, divided by 0.8, and then take the square root. We get 624.3 meters per second. Alright, so that's the internal energy. The next thing we're going to look at is specific heat. And this deals with basically how much a substance is resistant to heat change. So, specific heat capacity is the quantity of heat required to change the temperature of a unit of mass, a substance by 1 degree. This is the characteristic of the substance and is the resistance of the substance change to temperature. So, for example, if a substance has a high specific heat, that means it takes a lot more energy, a lot more heat to change that temperature just a little bit. If it has a low specific heat, it doesn't take as much energy to change that temperature, so it changes a lot easier. So it's less resistance. But one thing I want to mention is the units. You want to make sure when you do the calculations that the units match the temperature and the mass. Mainly the mass. The temperature, Celsius and Kelvin, a lot of times we're going to be dealing with temperature change. That's just something you got to keep in mind too. But if we're dealing with temperature change, Kelvin and Celsius may not matter because the change is the same. Just if it's in Fahrenheit, switch it over real quick. The mass though is important, right? So we see here different tables. This is calories, grams per Kelvin. We also have BTUs, pounds per Fahrenheit. We don't really deal with that. Your molar C, joules per mole Kelvin. You also have joules per gram Kelvin. We can also do kilojoules per kilogram Kelvin or kilojoules per gram Kelvin. It's all different units. The ones we'll stick with pretty much is in this column, but we may switch even these a little bit. If you have the specific heat, my suggestion is those are the units you go with. And then switch it if you need to at the end. If you don't have the specific heat and you're solving for the specific heat, then you can use the units you have and then convert them at the end to the units you need, um, if it's specifically asking for a certain unit. Right, so notice on this chart, water is the highest, and then ice and alcohol, and then everything else is under 1. That means water has the highest resistance. So you have to really add a lot of energy to get that to change. Then ice and alcohol take energy to change. The rest of these, which a lot of these are metal, a little bit of heat heats it up real fast. Okay, and think about it. You get in a pool, that pool can be out in the sun all day and it still doesn't heat up enough to burn you or anything. You touch metal, it's super hot if it's been out in the sun all day. So metal heats up a lot faster. Now, when it comes to gases, specific heat for gases depends on the process. So if it's a constant volume process, then we have what's the specific heat for the volume. So C sub V, and this is specific heat under constant volume. If it's a constant pressure process, then you have the specific heat for the pressure. Notice each of these gases have different constant pressure to constant volume. If you notice, the constant pressure is always a little higher, and that's due to just kind of what happens when the gas undergoes the process. Alright, so the way we're going to use this now is through calorimetry, which is something you may have seen in chemistry class as well. They probably were dealing a lot with the units in calories, but you will see it in chemistry as well. And before we get into a problem and different problems, I want to mention one thing with the difference between a closed system and an open system. A closed system can have energy exchange with the surroundings. So energy can go from this closed box to the air around it, and the air around it can put in energy from the air around it into the closed box. Okay, example would be a sealed container. So let's say you have a thermos. Put a little handle on it. So you have this thermos, right, and it's sealed shut as best as you can. And it's made to keep heat, but you're going to have some energy from the atmosphere come into it, and some energy from inside come out. What you won't have is you won't have the particles inside leaving, or the particles on the outside going in. That's a closed, sealed system. Open system be like just, say, a cup with the liquid. There's no lid, so you can see it inside the cup. Right? You have particles inside, you have particles outside. Okay? Not only can you have energy go out of the cup and energy from here come in the cup, but you can have a particle go into the cup and you can have particles go out of the cup. You can have what's called exchange of mass. That's the particles themselves. They have mass, so when they leave or enter the cup, then you're having an exchange of mass. And you have an open system. Right, so within a closed system, the energy in equals the energy out. Doesn't work as well with the open system. And so you have a conservation of energy. Most of the time, this is one of the labs that you really don't, you get a high error percentage because you can do everything you can, keep it closed, but once you go and take the temperature, you get particles leaving. And so we have conservation of energy. The energy lost from one part must be gained by the rest of the parts of the system. Okay, a lot of times if this is hotter, it's going to have, the energy leave. If this is cold, say you're trying to keep something cold, you have the energy come in overall. All right, so go and look at this example, and we have 2 bricks. I've been talking for a while, so let me check the time. 20. Okay, I got a little time before I switch and start a new video. So you have 2 bricks. You have 2 heated bricks, each of mass 50. So brick mass equals 50 grams. Yeah. One brick's heated to 40 degrees Celsius. The other brick, also mass is 50 grams, is heated to 50 degrees Celsius. You put the 2 bricks together in a closed styrofoam box. So this is the styrofoam box. And so we're sticking these bricks inside. Probably made the box too big. It's okay. I'm making sure they're next to each other though. Okay. So we put the 2 bricks in the box. The 2 bricks, the reason styrofoam is going to be insulated, the 2 bricks come to an equilibrium temperature of 45 degrees. So T final in here equals 45 degrees Celsius. We want to know what is the heat transferred for each block. So how much heat did this one gain and how much heat did this one lose? Okay, I can guarantee that's going to happen because this one's a higher temperature and they're both the same mass. And they're both brick, so they have the same specific heat, which let me get that specific heat. So specific heat mainly are either give it to you or you solve for it or you have a table that you can get from. It's 0.84 joules per gram Kelvin. Alright. This will come from some reference table. We have our masses in grams. We have this in grams, so that's good. This is going to tell us it's joules. Right, so the heat exchange, so the specific heat or the heat transferred in has to equal the heat transferred out. The heat transfer from brick 1 has to equal the heat that went into brick 2. So we'll just call it 2. But one has to gain it, one has to lose it, so we'll make one negative. Right, so we can rewrite these M brick 1, which I'm going to call this one M1, this one M2. Specific heat of the brick, which they're the same, so I don't have to relabel it, times your change in temperature equals, and we'll go do for the first one, equals the negative mass of the second times specific heat times the change in temperature of 2. These are going to be for each of the brick. So what I'm going to do is I'm going to do each of these separate. And that's why I have it divided in these different areas. So first we'll do the 50 degrees Celsius brick. So the mass is 50 grams. Specific heat is 0.84 joules per gram Kelvin. And the temperature for this first one goes from 45, that's the final, minus 40. Oh, we're doing 50, sorry. I'm thinking over here. That's the first one. 45 minus 50. Okay, so let's calculate this out. Times 0.84, and that's going to be a negative 5. I didn't have to switch it to Kelvin because, again, temperature change, still going to be negative 5. We get negative 210. The 40 degree brick is 50 grams times 0.84 joules per gram Kelvin. That reminds me, this is joules. And this would be 45 minus 40. That's going, basically all of these are the same. 50 times 0.84 times 5. We just don't have a negative sign. So this is going to be a positive 210. Okay, I'm going to stop this video here so it's not too long. The next thing we're going to do is I'll open this up with another example, since we're going to be dealing with a lot of the same stuff. And then I will go into this latent heat, and then we'll get into what's called transfer mechanisms, and then that'll be the end of the chapter. Alright, so I'll see you in the next part.